same process. We want to get y nth derivative equal to something that includes u. y2 dot is x2 dot. y2 double dot is x2 double dot, which is negative negative sine x1. y2 triple dot, negative sine x1, x1 dot. Y.
Cosine, right?
What?
Cosine?
Thank you. That would have gotten super confusing. Cosine. Y fourth derivative. I'm just going to do 4. Let's see. Minus cos x1, x1 double dot, minus plus sine x1, x1 dot squared, something like that. Plug in x1 double dot. Which is sine x1 plus u. Something like that, right?
Just why is it x1 dot squared? So I just don't see it.
This,
Yeah.
because when we differentiate cosine, we have to do chain rule on x1.
Oh, yeah, okay.
Yep. This part is our g, and this will be our f. So u1 is going to be negative 1 over cos x1 times minus sine x1, x1 dot squared plus cos x1 sine x1. I think I did that all right. And U2 will be our fourth order aerodynamics. Uh, 14641. Four lambda cubed error third derivative, 6 lambda squared error second derivative, 4 lambda dot plus lambda, oh, this is q, lambda to the fourth error, something like that, maybe. Okay, nay. All divided by negative cos x1.
You just run through how you got that integral expand,
Which bit?
just the U2.
All I'm doing is polynomial expansion on s plus lambda error to the n, where n is matching. So fourth derivative to the fourth equals 0.
Okay.
And then I am pulling out y to the fourth equals and putting everything else over here as my u.
Okay. Alright.
Why did you keep differentiating past the second derivative of y2?
because I need to get to you. And I only get to you when I plug in on x1 double dot. As a side note, if you find yourself having written u dot, you went too far. Right? So, internal dynamics on this.
Oh, I think, I'm just looking at you two, I think maybe the second term should be before lambda e third derivative. Is that right?
Yeah, yes. Yep. Thank you.
What did you say, Sophie? Was it E?
Not cubed.
Not cubed.
I have a question. So you got that y fourth derivative, and then you just got that whole f and g based on our general template, right?
Yeah, so I am, thing that multiplies u is g, everything else is f.
Okay, and then we just did like the whole f over g and all that.
Yeah, and u1 is cancel out f, which means you have to deal with, multiply by inverse of g and then minus f. And then u2 is multiply by inverse of g, put in your desired dynamics.
All right, because now the new system we care about is y to the fourth.
Yep.
Oh, okay, got it.
Yes. Oh, y2 to the fourth.
Oh, yeah.
Fourth order original dynamics, fourth order dynamics in terms of y. No internal dynamics. Now that we've set ourselves as controlling the angle of the upper cylinder, we can only drive that to 0 when it is sitting stationary on top, not spinning. We get the driving it to the top automatically because that's the only place it can stay at rest.
Can you say that slowly?
When we only cared about the angle between the centers, we can drive it to the top and have it sit there spinning, and it'll stay there. When we try to drive the upper cylinder to rest, the only way we're going to be able to do that is when it's balanced on top, not rotating. There's no way it can sit, having rolled halfway down, sitting still.
Are you getting to the conclusion because there's no internal dynamics?
Physically, set a cylinder on a cylinder.
Sure.
No matter what torque you apply to the lower cylinder, is there any way the upper cylinder can be at rest if it's not perfectly balanced?
Challenge accepted.
Right? Physically,
Right.
for the upper cylinder to not be rolling, it has to be centered on top.
Sure.
Right, the physics makes sense, but where do you get that from?
Yeah, where are you
This.
getting
Oh.
it from?
That's gonna come out to, there are no internal dynamics. We're driving everything to 0 when y goes to 0.
But where do we know that?
Fourth order system, y to the fourth. So there are no internal dynamics.
So no internal dynamics suggest the system is stable only when there's 0? The system.
We have chosen the dynamics for y, which is the dynamics for the orientation of this cylinder. When this cylinder is at rest, I probably have to do a little bit of work to prove that x2 is 0. Might not. That might come automatically. Short version, there are no internal dynamics. The system is stable and you've driven the thing you care about to 0.
I would say that system is second order. Why is it fourth?
2 second derivatives.
Two second derivatives, that's just it, okay.
Yeah, so x2 is second derivative of x1. So this overall system is fourth order.
Not satisfied. So when the question asks, like, describe the motion they represent, I guess I'm not really understanding what it physically means to not have internal I mean, it just means that whatever input I put into the system will be that input. There's no additional.
You remember in 205 when we talked about canceling some piece of the plant dynamics, but it's still there in some other
Same whole
output?
zero cancellation.
This is, when we choose X1, X2, the orientation of our upper cylinder doesn't show up in the dynamics that we're driving to zero. And so we can successfully drive the system we started talking about to zero, and that is angle between the centers. We can drive that to zero, but we made no mention of what the orientation of the upper cylinder was going to be. And if we do this, the upper cylinder will in fact just keep turning. The internal dynamics is that we didn't, in the output we chose, we didn't capture the dynamics of the upper cylinder. So they are internal.
In the first control, so you have the bottom cylinder rolling,
Mhm.
the top cylinders rolling against each other. They're both vertical.
Yep.
Okay. And then on that bottom one, only the top cylinders control the bottom ones is freely spinning.
In the second part, we've chosen our output as the angle of the upper cylinder. We're still applying torque to the lower cylinder.
Oh.
It's the same physical system,
Got it.
same input point for our torque.
Oh, yeah, okay.
But by driving the upper cylinder to come to rest, we are going to also drive the lower cylinder to come to rest.
Got it. So it's a better control system.
Part C, which one would you choose?
Oh.
So second one is better because there's no hidden internal dynamic.
There's no internal dynamics. If the internal dynamics were stable, then it would be a fair choice to say choosing a system with unstable internal dynamics is a bad plan. Let me put it that way. Again, I come back on the side of their cylinders, they can roll forever, that's fine. But the official answer was the second one is better because it doesn't have unstable internal dynamics.
So let's say you had like some different formulation or some different equation for your internal dynamics, you would just test it with Lyapunov. and you
Yeah,
could say
is it
was-
stable?
Okay, just do some, this
You can
first
do
method.
first method, you can do second method.
Yeah.
If you've got any kind of an obvious argument for why it's unstable, that's a
Yeah.
problem. If you've got any proof of stability, that's great. If you've got it stable but only at a point, then you might need to do some more work, but I would also come back to that question later because you've already done a bunch. Right? Seriously. They're fun. You get fun
For you.
problems. No, they're not
They're
fun.
not fun
I have
for
to
you.
agree. You should know that. All right, last question, unless there's anything more people want on this. Feel free to ask Rock questions about this on Tuesday also. Just saying.
So I think when we were talking about this stuff in class, we would, to look at the internal dynamics, we would go back to the equation for the other variable that wasn't our y,
Yes.
and then we would plug in for the things on the right-hand side, and then
Yep.
see what we got.
And you can use arguments around we have chosen to stabilize y, so any variables included in it are going to be driven to zero. So y is x1, we're driving x1 to zero, x1 dot's going to be zero, x1 double dot, etc. All of the x1 variables are going to have to go to zero for x1 to be zero.
So then for the other one, if you tried to plug in for like the x1 double dot equation, can you just not do that? Because it doesn't make sense in this one, because
You
the order
should,
matches, or would you just get like 0 equals 0 or something?
no, you should get that it's stable. So this term here minus sine x1 is going to cancel sine x1. Then we've got minus sine x1 dot squared, which is going to be positive, over cosine x1. It's going to turn into a bit of a mess because this error is in terms of x2, but it should come out that it's stable.
But, okay, but you said there is no internal dynamics.
Right. This is not internal dynamics.
Oh.
This is dynamics of the system.
Mhm.
And because we chose stable dynamics, we should be fine. I was wondering, I was looking at it to see if it was going to be quick and nicely fall out, and the answer is no, it's going to turn into a pile of math. But fourth derivative, fourth order system, no internal dynamics is the very short answer on part 2. Yes. I'm going to erase this, and we're on to the last one.
Did you answer the part C, which design would you use?
Again, the official answer is that that's unstable, and choosing an unstable system is bad. And the only way you can get away with not choosing that is to comment on the nature of cylinders and their ability to roll forever. But in general, if you've got something that isn't stable in the sense of Lyapunov, and you've got a choice for something else, take the something else. Problem 5, what are we asking?
Consider the system defined by x double dot equals u plus capital B. B is an unknown but constant disturbance within the negative x max to x max.
Yep.
And design a sliding mode controller.
Part A was intended to be a gift.
Part A,
Part A was intended to be a gift.
5.
So it's negative u, or negative b, I guess. Fine.
Like I said, it was intended to be a gift.
5.
So is the plant just like nothing?
The plant is x double dot equals
U plus capital D.
u plus d. Yeah.
Which in our control law includes some sort of cancellation.
Negative D.
We don't know d.
Okay.
We have a bound on d, but we don't know it.
Oh, so you don't, I guess you can't include it.
Yep.
How many people were like me?
It was intended to be a gift. Most people did this no problem. A few people worked really hard to try to come up with some kind of a cancel D thing, and it didn't go well. All right, sliding mode control though. If there's nothing dynamic C in terms of X to cancel, it's really straightforward. Or at least it should be. Part B, what are we doing?
Wait, why was double gift back?
Because this is all you had to write for part A.
Is that an S? That's an S.
Yes, this is S, but
Why?
capital fancy script.
Sure.
Why is it not a D thing?
D is an unknown disturbance.
Okay. Right.
When we do sliding mode control, we're going to size delta to be big enough to deal with our unknown disturbance. It's not a plant dynamics that we're going to try to cancel. Part B, in fact, was how big delta to guarantee stability, right?
Yep.
B,
Guarantee that the system will slide along the surface.
yes.
Really?
Yep.
That's it?
Yep. If you want, you can prove it with Lyapunov. And I don't remember whether or not Rock did in the solutions.
Oh, I did Lyapunov.
Oh, right, D naught was the bound. Right, we are given D naught bigger than D. We don't know what D is, but we do know D naught. Right? That's A, that's B.
Yeah, if you include a D in your U, it
Oh,
cancels
yeah.
out in your B, so you get so you get delta bigger than 0. Anyways, never mind. Sorry, go ahead.
Yeah, no, if you tried canceling your unknown, it went poorly.
Yeah.
That was it for B.
Is it always the case that you're in sliding mode control, your delta, if you know the bound for your noise? Because I think that was the case for your homework, our homework as
Yep.
well. That
So in the homework, it was, what, delta bigger than
like epsilon.
epsilon